Hello again. So now that we've developed the product and quotient rules, let's see some examples of their use outside of just strictly differentiating functions. Let's see some applications. So our first exercise here asks us, where is the function 1 plus x divided by 1 minus x increasing? Where is it decreasing? We've seen problems like this before, and what we understand is for increasing and decreasing, what we want to know is, where is the derivative positive? Where is the derivative negative, respectively? So the first thing we're going to have to do is calculate the derivative. That is a quotient. I can't really simplify it. There's no special tricks I can use here, so let's just apply the quotient rule. So alright, so differentiating the top, the derivative of 1 plus x is 1. Leave the bottom alone, 1 minus x. Subtract. Leave the top alone, 1 plus x. Differentiate the bottom. The derivative of 1 minus x is negative 1. And then I'd have 1 minus x squared. Alright, so f prime of x then is 1 times 1 plus x. That is 1 minus x. Now be careful here. I have minus 1 times negative 1. So that would be a plus 1. And then I have a minus x times negative 1. So that's a plus x. All divided by 1 minus x squared. Alright, so then this simplifies as, let's see, 1 minus x, that's 2 over 1 minus x squared. So now we need to know, where is this 2 over 1 minus x squared? Where is it positive? Where is it negative? Alright, so if you remember how to solve this, this is basically a rational inequality. Right? We want to solve, where is 2 over 1 minus x squared greater than 0, and we want to know, where is 2 over 1 minus x squared less than 0. That's what we need to solve now. Okay, so remembering how to solve rational inequalities, we have a rational expression. We want to know where its numerator could equal 0, where its denominator could equal 0. Any zeros of the function, any places where the function is undefined. And so looking at this, I see that x equals 1 causes the denominator to equal 0, and that's the only important number. So if we think of our number line here, 1 is an important number, and then there are no stationary points because the numerator could never equal 0. It's 2. And so then what we would say is, well, where is it? So let's test a value. If we test, how about 0? Let's test 0 in. We would have 2 divided by 1 squared, so that's 2 over a positive number. And so that's a positive number. Positive. And then let's test a number greater than 1. How about testing 3? If we tested 3, we would have 2 divided by 1 minus 3. Now that's negative 2, but squared is positive. And 2 divided by a positive number is again positive. And so what we see here is that the derivative, right, testing into the derivative, f prime of x, the derivative is positive over both intervals. So what I can say here is, the function is increasing on negative infinity to 1, and then again on 1 to infinity. The function never decreases. Let's develop a few more, or a couple more derivative rules. Let's find what's the derivative with respect to x of the tangent function. Now, we're not going to go back to a limit definition for this like we did for the sine and the cosine functions, because we know that the tangent function is expressed in terms of the sine and the cosine. The tangent function, right, this is the same as writing d by dx of sine x divided by cosine x. And now let's apply the quotient rule. So let's apply the quotient rule. I'll put a little QR there for quotient rule. Applying the quotient rule, then differentiating the top, that would be cosine x. Leave the bottom alone, cosine x. Minus, leave the top alone, sine x. Differentiate the bottom. The derivative of the cosine function is negative sine x. Over the bottom square, cosine x square. All right, so that gives us then cosine square x plus sine square x divided by cosine square x. And then if you remember a rule, an identity from trigonometry, cosine square x plus sine square x, that's the Pythagorean identity, that's 1. So I have 1 over cosine square x. And if you recall another identity, that's equal to secant square x. All right, so what we can say is, our rules from what we've just developed is, the derivative with respect to x of the tangent function, tangent x, is the secant square function. Derivative with respect to x of tangent x is secant square x. Similarly, and I won't prove this one, but it would be a good exercise, we can prove that the derivative with respect to x of the cotangent function is equal to negative cosecant square x. All right, so these are a couple new rules that we need to add to our repertoire. Why don't you try and use a similar method like I just used to develop the rule for the derivative of the secant function. Now would be a good time to pause and try that one out on your own. Recalling that the secant function is equivalent to the reciprocal of the cosine function. All right, so secant x is 1 over cosine x, and applying the quotient rule. So applying the quotient rule, that would give us differentiating the top, 0, leaving the bottom alone, cosine x, minus, leaving the top alone, 1, differentiating the bottom, negative sine x, divided by cosine x squared. So then that would give us sine x over cosine square x. Now I'm going to break this up a little bit. Sine x over cosine square x, that's the same as 1 over cosine x times sine x over cosine x. And if you remember some identities from trigonometry, that's the same as writing secant x times tangent x. So, new rule. The derivative with respect to x of the secant function, secant x, is secant x times tangent x. Again, similarly, we can show, and I won't do it here, that the derivative with respect to x of the cosecant function, cosecant x, is negative cosecant x cotangent x. And again, these are 2 more rules that we should add to our memory. So now let's see an example. Let's say we wanted to differentiate h of t as t squared tangent t. All right, so here I see a product. So why don't you try this one out? Apply the product rule to differentiate the function h of t. H prime of t would be 2t times tangent t plus t squared times secant square t. And again, we could maybe factor this if we wanted to. We could factor out a t. So h prime of t we could write as t times 2 tangent t plus t secant square t if we wanted. See another application. Find the equation of the tangent line to f of x is 3x squared natural log x at x equals 1. Again, this would be a good time to pause and try this one out on your own. Did you try it on your own? I hope you did. You'll learn more from making mistakes than from just seeing me do it. Alright, so if f of x is 3x squared natural log x at x equals 1, we need a slope, we need a point to write the equation of the tangent line. Let's find the slope first. F prime of x is equal to 6x times natural log x plus 3x squared times 1 over x. At x equals 1, so f prime of 1 would be 6 times 1 times the natural log of 1 plus 3 times 1 squared times 1 over 1. Recall that the natural log of 1 is 0. So this becomes 6 times 0 plus 3 times 1, which is 3. And so that's the slope of the tangent line. We also need the point that the line passes through. So f of 1 would be 3 times 1 squared times the natural log of 1. Again, recalling that the natural log of 1 is 0, then f of 1 equals 0, and so our point is 1, 0. So taking that together, then the equation of the line we could write it in point slope form as y minus 0 is equal to 3 by x minus 1. So y equals 3 by x minus 1, or y equals 3x minus 3. For y is equal to cosine x divided by 2 plus sine x, find all x where the tangent to the curve is horizontal. Again, this would be a good time to pause and try this one out on your own. If we want the tangent to be horizontal, that means that y prime of x must equal 0. If the tangent is horizontal, the derivative is 0. So let's calculate the derivative. Y prime, we will need to use the quotient rule here. So derivative of the top would be negative sine x. Leave the bottom alone, 2 plus sine x. Minus, leave the top alone, cosine x. Differentiating the denominator. The derivative of 2 plus sine x, the derivative of 2 goes to 0. The derivative of sine x goes to cosine x. The denominator is 2 plus sine x squared. All right, let's simplify the numerator. Let's see, this would give us a negative 2 sine x, a minus sine square x, and a minus cosine square x. And the denominator we leave alone, 2 plus sine x squared. Now, we have a minus sine square x and a minus cosine square x. So notice that if I do a little factoring here, right, if I factor those terms, if I take out the negative 1, that is negative 1 times sine square x plus cosine square x. And we know that sine square x plus cosine square x is equal to 1 from the Pythagorean identity. So then y prime is equal to negative 2 sine x minus 1 over 2 plus the quantity sine x squared. So there's the derivative. That's our first part. Now we need to solve where is the y prime equal to 0. So let's solve negative 2 sine x minus 1 over 2 plus sine x quantity square is equal to 0. All right, well, a fraction equals 0 when the numerator equals 0 and the denominator is non-zero. Now, 2 plus sine x can never equal 0. Why? Can you explain why that's true? 2 plus sine x can never equal 0. Think of the graph of the function. I'll give you that hint. All right, so if we wanted to solve this equation, this is then equivalent to writing negative 2 sine x minus 1 equals 0, which then implies then that sine x is add 1 divided by the negative 2, negative 1/2. So then we just have to say, well, where is the sine? Negative 1/2. And we weren't given a restriction on the domain, so we have to think of all possible real values. So sine x is negative 1/2, so then that implies that x is equal to, we have two fundamental solutions at 7 pi over 6 and 11 pi over 6. And we could take any of those and add k times 2 pi, where k is an integer. All right, so we have our two fundamental solutions. Those are the solutions over in a sense, the first rotation about the circle. But then we could get many more, infinitely more x values just from the periodicity of the sine function. Where is the function s of t equals t squared times e to the t increasing, and where is it decreasing? Good time to pause. Try it out on your own. We've seen problems like this before. To answer where a function is increasing or decreasing, we need to find the derivative, find where the derivative is positive, find where the derivative is negative. Let's calculate s prime of t. Applying the product rule, I would have 2t e to the t plus t squared e to the t. And I think we actually calculated this derivative earlier in the section. So then I can factor this. I can write this as t times e to the t times 2 plus t, if we wanted. All right, so now we need to solve where is s prime of t. We want s prime of t to be positive. We want s prime of t to be negative. And in answering both of those, it's useful to first find, well, where is s prime of t equal to 0, if possible. So let's solve s prime of t equals 0. We already have the factored form, t times e to the t times 2 plus t. So if we set that equal to 0, notice it's already in this nice factored form. So now, using what we understand from, in a sense, from polynomials, but if we have a factored form equal to 0, we can set each factor equal to 0. So this tells me then, so t equals 0. Well, that's nice. E to the t equals 0. E to the t. The exponential function is asymptotic to 0, but never actually equals 0. So e to the t equals 0, that's not true. That's invalid. It doesn't give us any solutions. But 2 plus t can equal 0. If 2 plus t equals 0, that means that t is negative 2. So for our number line, we have two important points. Right? If we set up our number line and test, we have negative 2 as an important number, we have 0 as an important number, and we need to test each of these three intervals. And now let's test into the derivative s prime of t, and I'm going to use the form t, e to the t, t plus, what did I write? 2 plus t. And one thing to remember here is that e to the t, that second factor, this e to the t, is always positive. E to the t is always greater than 0 if t is a real number. So that makes life a little bit easier for us. So let's test, I don't know, negative 3. All right, so testing negative 3, sorry, not f, what did I call it? S. S prime at negative 3 would be t. Negative 3, so that would be a negative. E to the t would be a positive. And then 2 plus negative 3 would be a negative 1, which is negative. Negative times a positive times a negative is positive. Positive over the first interval. Okay, then from negative 2 to 0, how about negative 1? S prime at negative 1. T is negative 1, which is negative. E to the t is always positive. 2 plus negative 1 is positive. So now I have a negative times a positive is negative. Now, testing a value greater than 0. How about positive 1? S prime of 1 would be t is 1, which is positive. E to the t is positive. 2 plus 1 is 3, which is positive. Positive times a positive is positive. Where is the function increasing? That's where the derivative is positive. Where is the function decreasing? That's where the derivative is negative. All right, so answering. S of t is increasing on the intervals negative infinity to negative 2, and then again on 0 to infinity. S of t is decreasing on the interval negative 2, not to infinity, but negative 2 to 0. Again, this is not really a new exercise. We've been doing this concept for a couple sections now. The only difference is now we can use a new type of function. All right, so let's finish off with one more exercise. A little strange because I'm just going to give you some information here. Suppose that f and g are differentiable, and we know that f of 3 is negative 2, g of 3 is 6, f prime of 3 is 7, and g prime of 3 is negative 1. If h of x is x to the 4th times f of x, find h prime of 3. I want you to try this one on your own. So now would be a good time to pause and think about this and notice that h of x is a product, and see if you can do something with this exercise. So h of x is a product of functions. It's the product of x to the 4th and f of x. So then h prime of x would be 4x cubed times f of x plus x to the 4th times f prime of x. That's from the product rule. So that means that h prime of 3 would be 4 times 3 to the third times f of 3 plus 3 to the fourth times f prime of 3. Now it's just arithmetic, and knowing that f of 3 is negative 2 and f prime of 3 is 7. So let's see, 4 times 3 to the third, that's 4 times 27. Let me use a calculator here because I don't feel like doing that arithmetic in my head. 4 times 3 to the third, that's 108. So that's 108. F of 3 is negative 2. 3 to the fourth is 81. And f prime of 3 is 7. So I've got 108 times negative 2 plus 81 times 7. I get 351. H prime of 3 is 351. All right, so that's how I would do that first exercise. So now that you've got that, why don't you try this second exercise? M of x is x times f of x divided by g of x. Find m prime of 3. Now's a good time to pause. This one's a little tougher because we have a quotient, so we're going to have to use the quotient rule. But if we look in the numerator, if we look at that x times f of x, that's also a product. So we're going to have to use the product rule as well in one of our steps. So it's a little bit tougher. All right, let's calculate m prime of x. M prime of x would be, let's see, I have a big fraction bar here. All right, so now I need to differentiate the top. But in differentiating the top is x f of x. I'm going to have to use a product rule here. So the differentiating x f of x, that would be 1 f of x plus x f prime of x. That's just the derivative of the top. Times g of x. Leave the bottom alone. Minus, excuse me, minus. Leave the top alone. X times f of x. Differentiate the bottom. G prime of x. Divide that by the bottom squared. Whew, that's a mess. That's okay. Now we just need to go through the substitutions and the arithmetic. So let's see, that would give us then, so now m prime of 3 would be 1 times f of 3 is 7 plus x, that's 3 times f prime of 3 is, oh, I made a mistake already. 1 times f of x. F of 3 is negative 2. Sorry about that. 1 times negative 2. Plus 3 times f prime of 3 is 7. Times g of 3 is 6. Minus x f of x. 3. F of 3 is negative 2. G prime at 3 is negative 1. G of x squared, that's a 6 square. Alright, so now we got to just clean this up. Let's see, that's negative 2 plus 21. That's 19 times 6. That's 114. Oh, then we got several. We have minus, 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 so that's a minus 6 over 36. So 114 minus 6 is 108 over 36. And if I'm not mistaken, that's exactly 3, isn't it? So it turns out to be 3. How fortunate. Alright, so m prime of 3 is 3. And that concludes this video and this topic on the product and quotient rules. Alright, so coming up next, we're going to develop another rule. Actually, we're not going to develop it so much as accept it. We're going to accept another rule that allows us to find the derivative of composite functions. And that's called the chain rule. So that's where we're going next. Hope to see you then. Have a great day.